All right. Welcome, everyone, to another installment of the Trino meetups. My name is Brian Olson. I am a developer advocate at Starburst, and I just wanted to do a quick round of intros before we hop into the meat and potatoes of the subject today, which today we'll be getting joined by Andre Rosa. He is one of the engineers behind the project Tardigrade, which was the initiative to essentially add fault tolerance capabilities around Trino to basically make it a lot more easy to adopt as a batch query engine. And so there, and among other reasons, right? Sometimes there are resource contention, things like that. And so what he'll be talking to you all about today is getting into calling this extract Trino load, which is the common the common why can't I think of the name for when you abbreviation, the common abbreviation for extract transact load. And so we're basically saying Trino is a very solid system to use for that transactional part of the ETL, and particularly very suited for batch querying. It always has been, but now with fault tolerance capabilities, we think it's going to make it a lot easier for the general public to set it up and use it for these purposes. So really excited to dive into that. Before we do that, here's the quick agenda that I have. I just a couple community things I'm going to talk about, and then surprisingly today, unfortunately for those that are huge Need2 fans, I will be the one doing the Trino and Starburst overview as well. Need2 is out with a cold today, so she will come back hopefully ready and excited in July to tell all of our Trinoobies and folks that are not familiar yet with Trino what Trino is and what Starburst is. So I will be doing that today, though, and then after that I will be handing it off to Andre. And so let's get jumping right into this. So quick round on community. If you are new to this community and you want to know kind of where to get started, the de facto place that we typically send almost anybody is to our Slack channel. Obviously, go to our website, trino.io. But then if you're looking for a place to interact and find people, a lot of us are just basically sitting around on Slack, just waiting for new community members to come in and ask us really intriguing and engaging questions. So definitely hop onto Trino Slack. It's at trino.io/slack.html. And essentially, you'll join up if you haven't joined a Slack before. Basically, it'll just ask you to basically have some sort of sign-in method, and then you'll join the Slack channel. Likewise, if you're not necessarily wanting to just go directly talk to a human, but you like hearing me talk, as well as I have a partner in crime on this next little bullet point here named Manfred. Me and my friend Manfred are basically just talking about cool things going on in the Trino community on this show called Trino Community Broadcast. And what we do there is we break down different things, either about the core Trino query engine, Trino ecosystem, architectures, things like that. And just also give updates on release notes and show cool, fun little demos. So if that's kind of your style and you like to kind of listen to things in like a YouTube or broadcast type manner, go to trino.io/broadcast, and we have a whole bunch of episodes for you to catch up on and check out there. You are here now in the Trino virtual meetups, but we do have them currently split out into 3 regions. This is currently the Americas. We are scaling up some in the EMEA, and in the near future, we'll be scaling up some in APAC. So if you have friends in that region, or you are in that region and you're currently just tuning into the Americas, thank you for joining, from being from all across the other side of the world. But we'll hopefully be having a lot more locally in your area in the coming months in the coming months. So if you want to learn how to contribute, if you've been wanting to contribute to an open source project, go to trino.io/development. And then, you can also do this in the form of contributing code. You can also contribute documentation, which is also like kind of sitting with the code. And then there's also ways that you can contribute otherwise, being on Slack and answering people's questions, or joining the writing a blog essentially and contributing that. Those are all ways that you can actually contribute. And so these are all kind of links that if Anna, if you could add that into the comments here in a second. That way, the nice folks at home don't have to necessarily really quickly write all this down. So yeah, so that's one way. And then another final way, and this is relatively not as new as it was whenever I first put this whole separate slide up. Another very engaging way to start getting involved with folks is Trino Forum. Thank you for that, Anna. And so basically that resource that just came up has all the community resources that I'm sharing with you right now, all on one page. So basically the Trino forum is a discourse forum. You might, not to be confused with Discord. It's kind of your typical question and answer forum, kind of like Stack Overflow, but we do a little bit more with it. We also make it places where people can just kind of post their projects and kind of tutorials. And it's also just a really cool way to kind of have core people that are, kind of sitting there talking on Slack. But essentially, when we have these conversations there in Trino forum, this gets actually picked up by Google, and it makes it a lot easier for new folks to find good, like all these answers. Unfortunately, Slack kind of keeps it a little hidden away. And so we're trying to actually kind of expose some of those conversations in Slack and organic conversations that are coming up within the Trino forum itself. So definitely take a look there, and I would love to have you on that forum as well. Finally, for joining here today, if you have not gotten one of these awesome Commander Bun Bun t-shirts, this link here is also included in that community resources. You just got to click on this URL down here, and then sign up for whatever size shirt you need. And provided that you are in one of the areas that we can ship to, then oh yeah, here we go. Thank you again, Anna. Yeah, sweet. So that one is also now added in the YouTube comments. So click on that, fill out the form, and if you're in an area that we can actually send these to you, which a good chunk of you should be, then we'll send that to you. Otherwise, we'll send you a gift card. Great. So any questions, obviously during this talk or after the talk, do let us know in either the YouTube chat, and of course, after the talk, please check out the Slack. And then for other questions that you want to more generally pose, definitely we'll take it on Trino on Twitter. If you follow us at TrinoDB, and just or kind of tag us, that is the handle that you can use. So with all that, I will then go on now to the typically need to section, which is going to be what is Trino and what is Starburst. So if you're new here, welcome. Let me do a quick little rundown about our this software that we're so excited about and so passionate about. So Trino actually was not originally called Trino. It was originally called a open source project called Presto, and was recently rebranded in almost a year, getting close to a year and a half ago. Now it was rebranded to Trino. The three original founders were working at Facebook, Martine, Dane, and David, as well as actually there's kind of a fourth who joined the project like right after these three started it, named Eric Huang. So those four members basically started out with Presto. We're filling in this void of, Facebook was facing a lot of like slow analytic issues using Hive at a high scale of actually the data warehouse at the time was 300 petabytes. I'm sure Andre has better stories of his time at Facebook, was probably scaling up way higher than that. But they were trying to run these very interactive analytic queries, and had a lot of data scientists and even data engineers that were trying to kind of do experiments, and we're having to wait, hours to days for these queries to finish. And so Presto was a way to solve for that. One of the initial things that these three wanted to address from the beginning is they knew that making a healthy open source project rather than keeping this something internal in Facebook was going to be something very core to how they could make this software successful, by not only just taking in the needs of immediately Facebook, but also trying to get in a lot of the direction and help from companies initially in the Valley, but now has grown out to quite a few more. Um, so let's talk about what actually is Trino. So Trino, as opposed to kind of its Hive predecessor, it's an MPP SQL query engine, and so as averse to Hive was basically an abstraction layer of kind of SQL that was essentially being generated into these MapReduce models. So MPP is a lot more tightly integrated with things that are essentially couples much better with SQL, and has a lot of these operators that are very pipelineable and work really fast in terms of avoiding any types of blocking and things like that. So it makes this query engine very super fast. So Trino has now proven scalability up to multi petabytes, has run in a whole bunch of big companies in the Valley, and has also been a very more and more adoptable project by mid to low level, even startup companies that are really starting to take advantage of the benefits there. It's super community driven open source project. One of its greatest achievements is the fact that this query engine was something that is essentially constantly taking in innovation and change and issues and new direction from the community, and trying to basically stay the course of not trying to focus on a particular smaller set of problems. It's essentially trying to keep up with changes in how people are using this software. Separation of compute and storage is core to, I think, any very successful query engine these days, and Trino is definitely no different there. You obviously want to scale storage and compute separately, but then there's this extra added benefit that Trino has on top of just splitting those up. It has a lot of this ways to abstract the connections across these different storage layers. So you can have, Hive, which was the original one that they were replacing, but now you can actually connect to RDBMS solutions like MySQL, Postgres, or NoSQL solutions like Mongo and Elasticsearch. And you can actually run queries across all of these different data stores. And then finally, you can deploy this anywhere, cloud, on premise. Works very well in cloud now with a lot of S3 integration. And taking advantage of Kubernetes. There's a open source Helm chart now to actually deploy all these. So that's what Trino is, but what is Starburst, and who's paying me the money to actually sit here and talk to you about this awesome open source project? So Starburst is a distribution of Trino, and actually a couple distributions. In fact, we have an enterprise product called SEP, Starburst Enterprise Platform, and then there's Starburst Galaxy. And so SEP is kind of still very similar to a similar deployment that you would have with Trino, but instead we have extra connectors, a lot of modified security and enhanced capabilities around security, but then you also have obviously then the support and a lot of extra small little bells and whistles in there that from a deployment aspect we make it a lot simpler. Starburst Galaxy, on the other hand, is what a lot of people are kind of in the cloud environments are much more apt to expect these days, which is it's a SaaS offering version of Trino. So instead of having to deal with scaling and all these other things that you typically have to think of when you do this deployment, Starburst Galaxy takes that kind of like pain away from you. So you're able to just use Trino. You're able to scale it up as you need it to, and you don't have to be doing all the heavy lifting to actually manage that infrastructure. So it's really exciting to have options like that, especially for those kind of like companies that don't have the full-on engineering crew to really be managing a lot of this stuff that the Silicon Valley folks are. So ultimately, this is a very busy slide, and so admittedly, I always get nervous when I see slides like this. I don't know how to even begin talking to them, but you think about this is like you have a lot of people that are using kind of anything from a BI type of use case all the way to data science type use cases, and so you have different people, different stakeholders that have all these various needs. You need to make sure that they are addressing specifically their needs and nobody else's needs, or having access to certain data stores or certain things that they don't need. So Starburst Enterprise and Starburst Galaxy really add a lot of these, like, data masking, data encryption, integrations with other companies like Amuda and all sorts of kind of bigger ecosystem partners that we have, that ultimately make a lot of this just like very much open up, get things connected, fill out some like GUI, and then click next, and you're done. And so, so this is kind of where on the enterprise side, where we kind of envision taking Trino and making it a lot more scalable, a lot more just taking a lot of the headaches away from our clients. So essentially, that is the kind of differentiation between what is Trino, what is Starburst, and I think I'll leave you with that. If anybody has any questions, feel free to leave it in the chat, and I'll be glad to answer. But now, the moment that you've all been waiting for, I would like to hand this over. Give me a moment, to Andre. Hey, Andre, how's it going?
Hey, doing good.
So yeah, really excited to hear about this. As I kind of alluded to, this is going to be talking about some of the work that you and the whole rest of the Tardigrade team. I'll just name a couple of them: Jobing, Lukash, Martine, Brian John, and I hope did I miss anybody? Josh Howard, and anybody else I'm missing off the top of my head of that team that is really heavily focused on this. No, I think that's about everybody, right?
Martin has been working closely with us as well.
Martin Traverso, right? Just wanted to say a huge thanks to all of you, and I'm really excited to hear about what you all have been working on, and take it away.
Hi, my name is Andre. So I'm a software engineer working for Starburst. I'm also a Trino maintainer. And today I'm going to be talking about Trino as an engine for large-scale batch ETL kind of processing. So a couple of words about the structure of this presentation. So first, I'm going to really quickly cover what Trino is, how it is related to Presto, what its relation to Spark, to Hive. Then we will also take a look into Presto/Trino history as an engine for batch ETL processing, and dive deeper into some of the challenges associated specifically with batch ETL processing as opposed to interactive querying. We will also discuss the new execution capabilities that we are working on, and discuss how all these new execution capabilities make it easier for us to kind of deal with all the batch ETL associated challenges. And at the end of the day, I'll try to cover the current status of this effort, what is available today, what are we currently working on, and what we are planning, and how are we planning to evolve it in the future. So first of all, like very, very quickly, like what is Trino? Trino is a distributed processing engine that allows processing very large data sets distributed over one or more heterogeneous data sources. And to do this processing, it also provides a very convenient and consistent NCSQL compatible interface, what makes this engine very powerful. To kind of better understand what Trino slash Presto is, it is worth mentioning its predecessor. So, like Hive was kind of a first attempt to provide a SQL compatible interface for large scale data processing. So before Hive, there was Hadoop, there was MapReduce, but in order to use MapReduce, you would have to write these jobs in Java or in like some other Java compatible languages, or there were some like other alternatives like Pig that had a different interfaces that wasn't very obvious and straightforward to use for everyone. So basically, with Hive, engineers were trying to address this problem. So with Hive, it was no longer needed to write, compile, and deploy Java code or try to understand all these other interfaces like the one that Apache Pig was providing. So large-scale data processing was as simple as writing a SQL query. However, underneath, Hive was still using the good old MapReduce platform from Hadoop that was originally designed mostly for this very long-running background processing. So queries written in Hive, they weren't really interactive. They were still taking long, and the experience was kind of the experience was not very interactive. So in Hive, it basically, to execute a query, you'll have to submit it. You'll have to wait for a notification that it succeeded, and then go and check the results. And it was bad if you went to check the results and there was actually an error, so you had to start this process over and over again. And the single iteration is taking like way too long. So there's like an anecdotal reports from data scientists that the data scientists at Facebook, then in 2012, they were able to execute only as little as 6 queries a day on average in interactive mode. So you can imagine how painful it was to do any kind of like data exploration or even debugging or improving their pipelines. So it was like clear that there is a need for better solution for interactive querying. So in 2012, Martin, Dane, David, and Eric, they started working on Presto also at Facebook, and they aimed to provide an alternative to Hive specifically for interactive querying. As the key design philosophies they set is the strong adherence to open standards. So there's no kind of HQL or any kind of SQL dialects or anything. So there was like a strong adherence to the ANSI SQL standard. So the idea was that anybody who knows SQL should be able to use this engine with no additional training or any additional problems. It also aimed to work out of the box. So they were aimed to provide like a consistent platform. So with Hive, you would still need like Hadoop and MapReduce, and you need to integrate all these pieces together to make it work. And this was supposed to kind of provide an out-of-the-box solution that you just deploy and it works. And an open source model with neutral governance was another key principle in this project since the very inception. As it is important when building this project, it is important to interact with broader communities to better understand what is needed and to move it forward. So for the timeline, so basically they started working on this project in 2013, and in 2012 and in 2013 there were first it was deployed in production, and the first interactive queries started coming in. But soon after that, engineers even from outside the Presto team, they built an integration with Facebook's batch processing platform, and they started sending batch ETL queries to Presto. So it happened like really quickly in less than a year. So like at first it might feel a little counterintuitive. It's basically, okay, there is Hive. Hive is built specifically for this like large scale batch processing. So it is specifically designed for that. Why would you use Presto for that? Right, and that's kind of like a very good question to ask. And there are mainly two reasons. So first of all, it was much faster, right? So while the latency probably doesn't matter that much for bad jobs, it is better if you can finish your job in 30 minutes versus an hour, or in like 15 minutes versus 2 hours. So the speed of processing definitely does matter. But there was also a second, I would even say not less important reason why people start submitting batch ETL jobs to Presto. And to kind of like give you a little bit of a perspective to the second reason, I'd like to tell a quick anecdote from my life as an engineer working on Presto, and how I used to work with data. So very often we had to diagnose some like slow running queries or some failing queries and so on. And for that, we maintained this data set called Presto Query Event, where a lot of like events from the Presto system were logged. And for each event, there was like a query ID attached. So what we could do, we could basically pull up these events by query ID, and that would provide us some information that we needed for debugging, like, you know, how much CPU time did the execution take, or maybe if there was any warnings, or if the execution was blocked or anything. So in order to kind of investigate like any slow running of failed queries, we went to this table, queried it by the query ID, and were able to come up with some conclusions. But as you know, like a system like Presto is integrated with many different systems, such as Metastore or a block storage where the data is stored. So sometimes the culprit laid in, like, you know, in the systems that Presto was integrated in. So what I had to do, I had to join data sets that were generated by Presto, that were generated by Metastore, that were generated by, let's say, the storage subsystem, to kind of to get necessary insights. And then basically an original query that used to run just a couple of seconds. After I started joining all these additional data sets, it can easily grow to run for like 5, 10, 15, 20 minutes. And where your query runs for like 10 or 15 minutes, it's kind of difficult to iterate quickly to get more insights, like, for example, to aggregate on different columns or to filter different things and so on. So to kind of get the interactivity back, what I used to do is to go and create a materialization. So basically create a background scheduled ETL job that would go and join a Presto data set with all the other data sets, let's say once an hour or once a day, depending on granularity. Generate a materialized table, so then I can simply query by query ID and get all the necessary information. It's just in a matter of seconds. And this was actually a pretty common use case, because very often, like, engineers or data scientists and so on, they had to join many different data sources together to figure out some insights. And now, in order to convert my interactive query that was already built, so I already had an interactive query that had all these joins, it had all the proper conditions, aggregations, and whatnot. In order to convert it into a batch pipeline, originally I would have to go and convert it to HQL. That was the dialect that Hive could understand. And as doing so, I would have to translate all the UDFs, convert SQL, and I would have to run it at least one time or more, depending on the situation, to check whether it produces the correct results. And all these steps are very time consuming because there's like intricate SQL intricate differences in SQL syntax. There are different set of UDFs, and of course it takes time to debug it. And there were even many cases where conversion wasn't possible. So for example, Presto was integrated with Presto was able to query data directly from MySQL, and then Hive didn't have a direct integration with MySQL. So if my original interactive query used to join some data sets from MySQL, and there wasn't even an easy way of converting this query to a Hive query. So the solution of running this scheduled batch jobs in Presto, it came out pretty naturally, because the only thing you need to do is basically just copy your interactive query, paste it into a batch scheduling tool, and you're pretty much done. So basically the second, as I said, not less important reason for running ETL in Presto was a unified SQL interface for both interactive querying and batch processing. But originally Presto was built for interactive that has its own set of challenges, but large-scale batch processing, it comes with its own set of challenges. And some of them are queries that require a lot of memory. So sometimes when you're doing this like large-scale processing, you want to run very large joins or very large aggregations to either create a dimensional table or differentiate the differential table. And you need to load a lot of data in memory in order to deduplicate or join or whatnot. These batch processing queries, they also tend to be more long-running, because in interactive, people usually not patient enough to wait more than like a couple of seconds. But for batch processing, queries can easily run for like 10, 15 minutes, an hour, or even like hours. And another big challenge was the resource management. Think of like a lot of these long-running, memory-intensive queries being submitted all at once by the batch scheduling system. So the engine had to be smart enough to know like what queries to prioritize, how many queries it can schedule at once to do not run out of resources, and so on. And in order to understand why these large queries are particularly challenging in Presto, it is important to understand how Presto executes queries. So in Presto, queries are split into a number of stages, and stages consist of like multiple tasks that are processing different chunks of data within a stage. So the data exchange between stages in Presto is implemented in a streaming way. So in order for the task to make progress, somebody has to consume its output. So what effectively it means that all the tasks from the same query have to run all at once. There's like certain corner cases when we can reduce number of tasks or number of stages running in parallel, but generally a mental model is that for general case they have to run in parallel. So with this model allows to achieve very low latency with no checkpoint overhead. So it works great for interactive. It is also very well crafted, so it scales quite well. It scales to like 1,000 node proven. However, at the same time, it is quite inflexible. So basically, it requires you to execute the entire query all at once and in an all or nothing manner. So the query can either complete successfully and fully or not. So there is no way of like suspending it or resuming or splitting this into a smaller chunk. It's basically like a single atomic unit that has to be executed all at once in an all or nothing manner. And so why this makes things complicated when it comes to like memory constrained queries or to long running queries or to resource management. So since all the tasks have to be running concurrently, so it effectively increases the amount of memory that must be available in a cluster in order for query to finish. It also makes it impossible to tolerate faults. So in case of any failure in any task, the entire query would fail, and this creates challenges for these long running queries. And the very similar thing is with resource management. So if somebody submits too many queries to a cluster, and at some point the cluster runs out of resources, it is impossible to kind of suspend one of the query or to deschedule it. It has to be killed in order to free up the resources and let the other queries proceed. So it could also be very wasteful from the resource management perspective. So how did we address this? How was it addressed at Facebook initially? So basically the idea was that, okay, let's just deploy these massive clusters, like 1,000 node each with 256 gigabytes of memory on each node. And with that big amount of memory, it is unlikely for a single query to run out of memory. This is just a lot of memory. Also with 64 vCores available on each node, it is hard to imagine what a query has to do to run for hours. So usually the queries tend to be not too long running with all these resources being available. So also resource management becomes somehow a simpler problem. So the idea was to limit a single query resource utilization to around like 5 to 10% of all available resources in a cluster. And then if you have this granularity, you can kind of try to manage resources at per query basis. And we also built this kind of history-based resource utilization prediction service. So based on history of previous run of a certain scheduled jobs, we could try to guesstimate resource utilization of a certain query and make some either admission or preemption decisions based on that. And with this approach, this approach has proven to kind of scale pretty well. So we were able to scale up to 10 terabytes of distributed memory per query, with like several CPU years utilized by a single query, and we were also able to run 80 queries concurrently on a single cluster. So it worked quite decently. So up until now, I've been mostly talking about Presta. So basically, now I'm going to slowly transition to Trino. So at Trino, just to understand what's the difference between Presta and Trino, I know Brian has already talked about this a little bit. So basically, Presta was started in 2012 by Martin, David, and Eric. And in 2018, they decided to leave Facebook and focus on building a community-centric project. So they created a fork called Presto SQL. It was later rebranded as Trino. but this is still the same project. So when I joined, when I decided to leave Facebook and joined the original founders as well as other contributors, key Rasta contributors or Starburst. I was kind of quite surprised to learn that Trino is not very widely adopted by the broader community for ETL and batch use cases. So together with Brian Jen, who also happened to be my colleague, my former colleague from Facebook, we run a number of customer interviews with Starburst customers. We also talked to a bunch of users from the Trino community to try to better understand why the community is hesitant of running this batch ETL workload in Trino. And as we run these interviews, we try to we started identifying some common patterns, and those were mostly like the same things. So basically, people were concerned about like memory constraint queries, long-running queries, and the resource management. So, for example, for memory constraint queries, it was often mentioned that usually somebody runs a 10-node cluster, but then there's like this single query that requires a lot of memory to process, and they need to upscale their cluster from 10 nodes to 100 nodes just for the sake of this single query. And then, of course, it is not cost efficient. Another one was like long-running queries. So in case if anything fails, they had to restart their long-running queries from scratch, and it was messing with their landing time expectations. And another big challenge was the resource management. It's basically people were expecting the engine to handle the admission and resource management for them. So the expectation was that I want to submit as many queries as I need or as I want, and this should be the responsibility of the engine to make sure that the cluster doesn't run out of resources and all these queries can eventually succeed. And of course, the workaround with deploying massive clusters wasn't really feasible because most of these community users, they run pretty small clusters. They run like 10, 20, maybe 50 nodes cluster, but nowhere near as like 1,000 nodes. And of course, they are not thinking about running like 80 queries concurrently to let us do the resource management efficiently. So it's not that like nobody in the community was able to use Trino for ETL. There were many companies that were actually doing this quite successfully. So one of them is Salesforce, and they actually have a very good article written about how they're doing this. The very quick summary is to basically keep it short and sweet. They are trying to avoid long-running and memory-intensive queries, and they are trying to structure their workload in a way that all the queries that they run in Trino are small and short-running. While this approach works for some companies, it doesn't work for everybody. So first of all, in order to pull something like that, you need a team of highly skilled data scientists and engineers to properly structure your workload. And in some cases, it may not even be feasible or possible to restructure your workload because some algorithms and some queries are simply not decomposable or not commutative. Think of like a yearly report of like unique users over the last year. So in order to address all these issues, we started to think. So we set our goal to kind of provide an out-of-the-box solution for ETL and to address all these problems that were identified. So the goal was to provide the necessary execution capabilities to handle queries of practically any size at a cluster with limited resources. And we also wanted to provide resource management capabilities out of the box as part of Trino. So basically the idea was that you submit your queries to us and we will figure out what to do. And you don't have to worry about overloading a cluster or anything else. So very soon we realized that existing execution model that is relying on this streaming exchange is just way too inflexible, and it's like it is going to be very difficult to be much better at these problems that we discovered with the existing execution model. Because with streaming, the execution model requires the entire query to be executed at once as a single unit, and it prevents us from applying more advanced execution techniques. So after careful consideration, we decided to actually remove this limitation. So the idea is to break down this streaming exchange limitation, and instead of having a streaming exchange, introduce a distributed buffer in between. So basically tasks are not directly interconnected. Producing tasks, they will be writing into a buffer, and consuming tasks will be reading from a buffer. And what it gives us, it allows each task in a query to be executed completely independently of any other. And this simple yet very powerful improvement opens a lot very interesting opportunities. So for example, when tasks can be scheduled one at a time, it reduces the amount of memory that must be available in a cluster to successfully execute a query. So in other words, it allows to run a memory intensive query on a much smaller cluster. So if you look at this slide, let's say if you have a query that has to run 6 tasks, and there is each task on average uses 20 gigabytes of memory. So with streaming execution, you need to have 200 gigabytes of memory available in your cluster in order for this query to succeed. But if you can execute these tasks one by one, you only need 30 gigabytes of memory in a cluster in order for this query to succeed. It also allows fine-grained failure recovery. So basically, with streaming execution, if any of the tasks fails, the entire query is failed. So the entire query has to be restarted. But if each task is independent, if it fails, you can start it over. Only a single task, because each task is this independent atomic unit that can be executed, restarted on its own. So being able to execute one task at a time in isolation also greatly simplifies the resource management. So for example, it is no longer needed to maintain an external system for predicting resource utilization for your queries. So estimating resource estimates can be done for a single task. And because as you can see, let's say if you have a query and you're trying to predict how much resources it will use, there's not a lot of information that you have. So basically the only information you have is pretty much how big is the data set this query is going to process. But it is very hard to judge about all intermediate stages, for example, how big of a join is it going to be, or how long the aggregation is going to take, or how much memory does aggregation need. So there are certain techniques that you can use, maybe cost-based model or maybe some other techniques, but they are all very unreliable. and the cost of a mistake is actually very high. So basically, if you made a mistake and then for what not reason and then if you try to run this query and you didn't have, you misestimated resources, and now you realize that you don't have resources available to run this query, you have to kill it and start it over. So you can waste a lot of compute resources. But if you are executing your query on the task granularity, you can estimate resources for this specific task. And for a specific task, you know exactly how much data this task is going to read. The number of operations within a task is also much smaller than in the entire query. So it is easier to predict resource utilization for a single task. Like for example, if you know that the task doesn't read, only reads 5 gigabytes of data, it's very, very likely it's not going to use more than 5 gigabytes of memory. And also if you make a mistake, right, it's not a big deal. So basically if you schedule a task and then there's no resources to run it and it fails, no problem. You adjust your estimate and reschedule just a single task. Resource estimates is just like one part of resource management problem. There is also the resource allocation problem. Resource-aware scheduling is also becoming much simpler problem when you can schedule at a task granularity, because it narrows down the question of whether I can run an entire query on a cluster to a question like if I can run this specific task on a cluster. So think about like a Trino cluster with like 5 worker nodes, and you know that you know memory utilization at every node. It is much easier to give an answer whether you can accommodate one more task than whether you can accommodate an entire query that can be multi-staged and pretty complex. And also the cost of mistake is much lower. So basically if you make a mistake with the all-at-once execution model, then you have to fail a query and start over. But if you make a mistake only at a task level, then the only thing what you lose is just the runtime of this small task. Another thing what becomes simpler is the resource sharing between multiple queries. So the scheduler pretty much just has to maintain an equal number of tasks running between the queries that are submitted in the cluster. So we're also trying to size tasks in a similar way. So basically we're trying to keep all tasks approximately of the same size. By size I mean the time it takes to process it. So it is easy to kind of rebalance resource utilization if a new query kicks in. And then in order to make sure that the resources are shared fairly, you just have to maintain an equal number of tasks running for all active queries. And it would be also possible and relatively easy to add different prioritization techniques. Like if there is like some high priority queries, then we may try to allocate more execution slots for that query than for the other. This new model also also makes it much easier to implement adaptive optimizations. Because queries can be suspended and replanned at pretty much any point, what you can do, you can let's say run your run a scan operation one table of a join, run a scan operation for the second table of a join, and if you see that it is a different join order is more optimal, you can swap them. You can also dynamically switch from like broadcast to partition join. You can handle skew. There's like many things you can do if you can suspend a query at any arbitrary point and replan. So the distributed buffer is designed to be fully pluggable with a simple, intuitive interface. So stripping out all the boilerplate, the interface is like very straightforward. So basically it provides a writer API that is invoked by tasks, by upstream tasks, and the reader API that is called by a downstream stage. And the API is pretty simple. For upstream tasks, it's just write some data for this partition, and for downstream tasks, it's just read this partition. So the API is like very, very simple and straightforward and easy to implement. For now, we provide a kind of like a proof of concept implementation. It is not like it is not production ready. It is production ready. We try to craft it in a way that that is reliable and everybody can use. But why do we call it proof of concept? It's because it comes with limitations. So currently it's fairly limited. It only supports up to 50 partitions, and it also requires a full barrier synchronization between stages. That is also pretty limiting, and I will talk about that more a couple of slides down. But while it is limited, it already allowed us to provide a ready-to-use solution that solves a number of problems. And it also allows us to, this pluggability allows us to decouple development of like scheduling primitives and core scheduling and from the development of a better solution for the buffering. So we can do more things in parallel and execute faster. So we're currently working on more advanced layered buffer implementation. So it will be designed to utilize distributed memory as much as possible before falling back to storing this data to disk or to distributed file systems. And this implementation is also going to be designed to support thousands of partitions. So we'll support like much larger queries, and it will also hopefully not require a full barrier between stages. And that would allow us to also try to address a more kind of low latency use cases in the future, because currently we are mostly trying to address this like background processing for batch ETL that is not as latency sensitive. But for more latency sensitive queries, once we have this like a better implementation that doesn't always touch disk and doesn't require full barrier, we would try to also address the low latency use cases as well with these new execution capabilities. So on importance of avoiding full barrier is basically think of a query like a limit query. So currently with Trino streaming, it can short circuit. So basically if a final limit sees that it received enough values, it can give a signal to the previous stage and say, okay, don't execute anymore, don't run it. But since currently our proof of concept implementation requires a full barrier, we actually need to run all tasks with partial limits, and only then we can run a final limit. So it actually slowing down some of the queries. As soon as we no longer require a full barrier in between stages, we can optimize it and achieve parity on that aspect with the streaming execution. Another interesting corner case is basically this thing. So let's say you have enough resources in your cluster to run 6 tasks, right? So with streaming, Trino would schedule all 6 of them, and all 6 will run in parallel. But with a fault tolerant execution, since today we require a full barrier, we first have to schedule 3 of them and then schedule the next 3. So it effectively may reduce parallelism, so some queries may start running slower. But once we no longer require a full barrier, we would be able to again run more tasks in parallel, so we should be able to achieve this parity. So Now, speaking about the current status. So at this moment, Trino already supports iterative scheduling. It supports failure recovery. It also supports the advanced fine-grained resource management. Trino also provides a proof of concept implementation for the buffer. It is limited, but it is fully working solution, and it's like it is production ready. There's actually several Starburst customers that are already enjoying it as part of our SaaS offering. So we are currently working, as I already said, on the better implementation. In the future, we are also trying to we will be trying to improve scheduling capabilities to better support interactive use cases and close the gaps that I just explained related to a full stage barrier that is currently introduced. So for the early results, with even the fairly limited proof of concept implementation of the buffering layer, we managed to achieve pretty good results. So we currently support join and aggregation that would otherwise require 5 terabyte of memory available in a cluster with only 100 gigabytes of memory available. So it effectively means that you can run a query that would require a 50 node cluster on a single node cluster. There are community members that were able to successfully deploy and run Trino on spot instances. So now, since there is failure recovery, you can try to run it on spot instances because you no longer care if a node would suddenly disappear. And some of them actually implemented some auto-scaling capabilities based on CPU utilization. I think it's like based on Kubernetes. And they reported to achieve up to 60% of cost savings operating Trino. The solution is also well battle tested under high concurrency. So we tested it with overloading it with a lot of resource-intensive queries with high concurrency, and all of them succeeded. So the resource management primitives are also there. They're well tested and are solid. So you're more than welcome to try it on your own and see and enjoy all these benefits. So as Brian already mentioned, Trino is a community-driven project, and we would love to hear back from you. So don't hesitate to join us on Slack as well to learn more about Trino and what are we up to by following our broadcasts, meetups, blog posts. Also, please give us a star on GitHub and join the discussion on the Project Tardigrade channel. This is the channel when we discuss specifically fault tolerant execution and all this new capabilities that I've just discussed. And if you and also don't hesitate to ping me on Twitter if you have any questions or if you simply want to say hi. Thank you for listening.
Thank you so much, Andrei. That was great. I'll actually be at the Open Source Summit next week in Austin and presenting there, so definitely looking forward to that. I don't see any questions in the chat, but as always, reach out if you have any. And yeah, like Andrei said, feel free to join the Trino Slack. And thank you again, and we'll see you next month.